Everybody, here you're looking at a microcontroller protoboard from one of my classes in school. This is from my Intro to Microprocessors class. This protoboard uses a Microchip PIC16F876A microcontroller, and on this board are different devices that the microcontroller can access and control as input devices or output devices. I figured since I'll be having to tear this board apart within the next few weeks, go ahead and bring it home for the weekend and do a video on it. I couldn't pass that up. As much hard work I've done on this thing, after all the lab assignments, pretty much every lab assignment consists of adding something to this board and programming it with a new program to do something else. Up here is a microcontroller. Again, it's a Microchip PIC16F876A. That's the microcontroller right there. That right there is actually a resistor pack. It's not a integrated circuit. It's just a 2x8 resistor pack. 330 ohms, and that's for the LED 7-segment display there. But anyways, this thing has an LCD display, the 7-segment display, has a keypad for input, a little speaker for whatever to actually beep when the controller is finished starting up. One lab we actually did play a very simple tune on it, but anyways. Over here is a stepper motor driver. Here is the driver for a AC Triac. This is actually able to control the brightness of a incandescent light bulb, kind of like a dimmer switch. Pretty much the same way. Had an isolation transformer, I believe. Or actually no, a pulse transformer inside of it. And the box. Anyways, down here, right in this area right here, is a circuit to run Pulse-Width-Modulation to a brush motor. I'll be demonstrating all of this. And here is a pot to control, let's say, the speed of a stepper motor, speed of the PWM, or let's say the brightness of a light bulb. It's an analog input for the controller. And it compares this with, I believe it's this one right here. One of these devices on here. I think it's this one here. Yeah, one of these devices is a voltage reference source. It takes in the 5 volts, sends whatever's not needed to ground, and sends an accurate 4.096 volts to the VREF on the controller, on the microcontroller, to more or less compare with the potentiometer. Just another little overview here. There's a bunch of wires. See, this is a proto board. Lots of jumper wires. The thing is, I have to get a close look at this thing because these wires like to come out. Can be very aggravating to deal with. And of course, when the jumper wires come out, things can stop working. This little microcontroller has 3 ports on it. You have your port A, your port B, and your port C. Some of these ports do different things, and you can configure, like, let's see, these here. I believe port A for analog or digital input. So anyways, that being said, let me go move over here to the 7-segment display. As there's only 8 bits on the port B, each digit has 8 bits. You have your 7 segments and the dot right next to the number. So how this works is the port B sends signals to turn on or off these LEDs, but port A has some leads to switch on and off these transistors here. So that way this controller can quickly switch through these digits here to make them look as if they're all running at the same time. This way it minimizes the amount of needed wires. And of course this little PIC doesn't have enough pins know-how. So that's pretty much the way you have to do things. That's kind of how the LED display works. Now of course with the LCD display you just have, I believe there's 4 bits going from this to this, and it has its own little integrated circuit on there that interprets what this guy, the microcontroller, tells the LCD what to do. So anyways, enough rambling on here. Let's go ahead and demonstrate this thing. What I'm going to do here is I'm going to load in some programs one at a time and do different things with this board. The first thing we'll do is load in a simple program that allows all these devices to work together. It allows the keypad to work with the LED display and the LCD display. So that being said, the way this works is to program this board you have to connect what's called a PIC. This is a PIC2, and you use software called MPLab, where you can either build your own programs or use it to load in programs onto this controller. I've already loaded in a program onto this controller. Now all I have to do is release it from reset, and you'll actually hear a beep, and you'll see text come up on the display, and just take a moment to guess what it will be. Okay, I'm releasing it from reset now. As you see it, guess what I put onto the LCD display there? Q Computer Company. Hey, what else do you think would be there? Anyways, go and hit C on his keypad here, and everything just magically disappeared. I'm going to show you what this keypad can do other than numbers. Obviously you can tell C clears it. Type in A, we get a colon. B gets a semicolon. C clears it. D gets an equal sign. E does greater than. F does a question mark. And of course 0 does 0. You can watch as I am typing on this keypad. You can see the 7 segment display show random characters. It's pretty typical. Basically after the controller finishes writing to the display, it has to clear the little 7 segment digit display, so that way you don't have these random characters on it. Now another thing I forgot to mention about this board is it can also sense temperature. And of course I'm going to demonstrate to you guys that this thing can run without this PIC2. Obviously it's a microcontroller, and microcontroller has its own program memory. It's like a little bitty computer pretty much. It's a little bitty 8-bit computer. It can't do a whole lot of things, and it runs on assembly language, but of course it is its own device. And let me go ahead and fix my tripod before it decides to fall on my circuit here. What I'm going to do here is I'm going to remove the PIC2 and plug in the power supply. And of course now power's off to this. I can go and pull this out. Now basically, for the power supply on this thing, it's located over here. That's part of the power supply. We have a 12-volt adapter. Now this controller runs on 5 volts. Everything on the circuit runs on 5 volts. And you're probably wondering, how does it do that? Over here, under this capacitor, is a LM. It is a ELN232 linear 5-volt voltage regulator. And basically what that thing does is it allows 5 volts to go to the circuit, but the remaining power goes to ground. So it's not very efficient. And if you overload one of these things, it will burn out. For an example, before we move on here, I just mentioned how this little guy here can burn out if you overload it. This is a couple days ago, before the Geek Fest, my instructor, he had a robotic arm which had a capacitor inside short out, and it left a big mess. It definitely overheated the little 7805 CT. Anyways, that being said, let's go and continue on. Plug in the adapter, and you'll notice here, as soon as I plug this thing in, it's going to start right up. There it goes. So anyways, this thing's running without the PIC16F876A plugged in. Functions just as before. Now you can't see anything on the display because I gotta clear it first. Let me show you how this thing is reset. There's a little button down here that's only active when this thing's running off of power. Hold it in, that resets it. Here's a different program. Again, I'm running this board off of the power supply. This program shows text on the LCD, runs a little clock here, which does have sort of a bug in it. I'll get to that shortly. Does see keypad input, and can read the temperature. Now let's figure out which device does the temperature. It's this one right here. What I'm pointing at right there. It looks like a transistor, but it's actually a sensor. It can sense the temperature of the external surroundings. And you can see it heats up when I put my thumb on it. So this right here is the voltage reference, and this is the sensor. Notice how it looks just like the PN2222A transistor right next to it. Anyways, the bug with this clock here, it's not actually a clock, it's just a little timer. But the bug here with it is, you can see there's no colon flashing here. Sometimes it flashes, other times it doesn't. It's due to a issue in the programming. But anyways, while we're on the subject of clocks, this PIC runs on 4 megahertz, and for clock circuits, this is not exactly 100% accurate. It's pretty close, but it's not 100% accurate. So let me go and explain why. It's because this PIC is running off what's called a resistor capacitor network oscillator. And let me go and get you that multi-sim circuit to show you just an example. Not the same circuit we're working with, but it's very close. It consists of a 3.9 kΩ resistor and a 33 picofarad capacitor. It's good for 4 megahertz, but it's not accurate. It's the cheap way of making an oscillator for your circuit. So anytime you're doing clocks, you always want to have what's called a crystal oscillator. For example, here's one on a computer motherboard. It's right there. It's a 20 megahertz oscillator, crystal oscillator. Crystal oscillators can cost considerably more, but they're more accurate for applications such as like a timer or a clock. That's why, you know, alarm clocks and stuff have them, and of course computers have them to keep the system time. So we're up to almost, let's say, about 3 minutes now. It actually starts at 1 minute when you release it from reset. So I'll hit reset. Starts right at about 1 minute 1 second. Anyways, demonstrate the little sensor one more time. Now we're going to move on to the next program. Okay, and now I've loaded in the program that does the PWM control to a brush motor. Can vary the speed using this pot. I'll let you have a close listen here. And you'll actually be able to hear the pulse-width-modulation. I don't know if any of you guys are familiar with RC cars, or you're probably more familiar with, let's say, cordless drills. They use this technology. So it might be a familiar sound to you. So anyways, we'll move on to the next program, which controls a stepper motor. It'll be the final demonstration on this circuit. Unfortunately, I can't demonstrate the light bulb, but I will include a little bit of footage from the Geek Fest of the board doing the light bulb. Okay, here is the stepper motor program. I'll get you a good viewing angle here. Do it from the side, that way you can see the pot and the little motor, little stepper motor. Go ahead and release this from reset. And you can see the motor is like freaking out. Actually gotta grab it so that way you can watch it. Not only does it actually step the motor, but it shows the value of what it's put into the motor on the display in hexadecimal. It does it from 00 to FF. And you can vary this with the potentiometer. And of course this varies the speed and the direction of the stepper motor. Watch it just speed it up. Gets it going pretty fast, and then, whoa, what happened here? Basically, the microcontroller is trying to control this motor at such a fast rate of speed that the motor can't keep up, so it just freezes up. Like this here. It's actually vibrating really fast. And of course I'll slow this down and it goes back to spinning. And I can slow it down. It starts getting slower and slower. And slower, to the point where it's going to be extremely slow. Now it's going in the opposite direction. And I'll speed it up, going faster, faster, and faster. And again, that's the same thing if I go too fast. The motor can't keep up. I was able to jump start at that time. It's spinning pretty fast now. So anyways, that concludes the demonstration of the stepper motor. And concludes the demonstration of this board. Anyways, now I'm going to include that footage from the Geek Fest of the light bulb. Here's the same microcontroller controlling an AC lamp. As you can see, I went and loaded back in the original, well, not the first program, but the one that does the temperature, displays, Q computer, and does the little clock. I figured while this is running, I'll go ahead and give you a final overview of the circuit. Because unfortunately, as I mentioned, I'm having to tear this apart within the next few weeks, so it's not something I get to keep. Get you a good close-up here of everything. There's the keypad, the speaker, right here is the stepper driver. You've got 4 2N2222A transistors here for switching on the poles of the stepper motor. And we've got these diodes here. These, along with this diode here on the PWM circuit, are designed to stop what's called inductive kickback, which can happen with any sort of inductive load such as a motor. When you cut power to the motor, what can happen is a reverse spike will occur as the magnetic field collapses, and without the diodes here, it would fry those transistors. So that's why we have diodes there. Anyways, that's the stepper driver. Again, PWM driver, very simple. Just a 2N2222A transistor, the diode, and of course we got the base is connected through a resistor to the microcontroller. And over here is that AC Triac driver. All of that circuit is pretty much going over to here. Have this diode. This blocks half of an AC sine wave. We got this. This is 0.1 microfarad capacitor, disc capacitor here. Another 2222A transistor here. Another 2222A transistor there. Lots of transistors, diodes, and resistors, and jumper wire in this circuit. I mean, this right here, in this little area, there's 8 2.2K resistors. There's another 2.2K, another 2.2K. This thing is slap full of 2.2K resistors. Here's a close look at the 7-segment display. Now these transistors here are not 2222A, they're different models. They're a little bit different. Again, all of the excess of jumper wire. It gets pretty messy. There's a tantalum capacitor. Reverse the polarity to one of those and you get a nice little pop. This capacitor here goes to the speaker. This capacitor is actually in series with the speaker. And I mean, from between the controller to this capacitor to the speaker to ground. If you have a close look here, you can see that oscillator circuit I was telling you about. You can see the resistor under the jumper wire, and there is the 33 picofarad capacitor. There is the reset hold button that's only active when this is powered off DC. I mean, this DC power supply, not the PIC 2. And of course, another 2.2 kΩ resistor. And the controller is actually powered from over on this side. There's actually a disc capacitor up under those wires. It's hard to see because there's so much stuff on this board. I mean, so much stuff. There is the LCD display. Looks just like the display you would probably find on a Texas Instruments calculator. And here's the main power supply rails. Pretty good sized breadboard. And it's slant full. I could probably cram in a couple more little circuits, but we pretty much got this PIC maxed out in terms of all of its pins. So anyways, any questions or comments, feel free to ask, and thanks for watching.